Go ahead, Artem.
Okay, thanks. I'm glad to meet everyone here on today's Journal Club. My name is Artem Karayev, and I'm going to tell you the main ideas of the article on the thermodynamic interpretation of deep learning systems with the authors Fioressi, Fainolini, and others, which you see currently on the first slide. So let's start. Firstly, I will tell you about the structure of the current talk. At the beginning, I will tell you the main goals and ideas of the article and what authors wants to show us, what results they want to see. Nextly, we will discuss we will discuss and I will tell you about the notifications, variables, functions, and other analytics which authors use to describe thermodynamics and deep learning. After this, I will tell about the experiments which authors use to show the results of and compare it with analytic, and at the end I will talk about the idea of authors by using contact Hamiltonian dynamics and their conclusions. First of all, I want to tell that as the main idea of this article and one of the main goals is to make a duality between the neural networks, machine learning, and well-known statistical mechanics and thermodynamics. So to find the parameters in well-known parameters such as loss function, learning rate, mini batch, and other in machine learning, and find their duality analogous in thermodynamics such as particles, mass, energy, temperature, and others. And here let's start. I will start with the definitions, variables, and functions which authors use. First of all, also I need to know that the terminology and notification sometimes is different from which we use currently now, and I will talk about it. First of all, they define the data set loss function, mini batch size, learning rate, and use common terminology for this. But the main object of the current article, the x vector, which they use x bar, and x bar means that this is vector. This is the author's terminology, and they use this vector x as the d-dimensional vector, where they collect all of the trainable parameters of the system. So all elements of weights, biases, or other trainable parameters are collected into one vector, and that will be the main vector which they will work during this research. Nextly, they define the gradient descent optimization in discrete and in continuous form, and they define the stochastic gradient optimization as the second equation, as where f with b index is the averaging of loss function over mini batch. And in other slides, I will show what are the differences in context of thermodynamics between gradient descent and stochastic gradient descent in the author's opinion. Authors look at this x vector as the sum position of the mechanical system at time moment t, and they introduce and they make first duality between mechanics and mechanics and machine learning. They say that they define the loss function as the analog of potential energy. and they define the force vector as the third equation at the minus gradient of potential. And so they connect at the fourth equation this force with some changes in velocity vector. Velocity vector is defined as the differences between as finite differences between states at t and t minus 1 moment of x vector divided by delta t. I need to know that delta during this research is not a Laplacian operator, it's just well-known differences between states. So the fifth equation, we see that fifth equation describes as well-known mechanics with constant acceleration. If we rewrite it in terms of potential energy, it will take the form of fifth equation. But after authors say that this equation is similar to equation of gradient and descent, as we see the delta x can be is equal to eta multiplied by nabla f and delta t. So if we take the velocity and set it to 0 before taking each step, we can find the first duality between mechanics, the second duality. First was potential energy and loss function, and the second duality, which authors define it, the duality between learning rate and mass term as sixth equation.
But Artem, hold on. You cannot just set the velocity to 0, because if you set the velocity to 0, then the state x doesn't change, and yet you want it to change.
Yes, I understand what you mean. The main idea is that they say that stochastical gradient descent doesn't optimize the velocity. It looks only at states. And this equation show and author through this equation wants to find the analog parameters in stochastical gradient descent and in well-known mechanics with constant acceleration. After this, as we see, the second analysis. Duality between learning rate and mass, and nextly they define the temperature. Instantaneous temperature, as I understand, is the temperature in the current moment t as the averaged as the kinetic energy divided by number of degrees freedom d. At the previous slide, they defined d as the number of all trainable parameters, and through this we can define the temperature at some moment t as seventh equation, where v are calculated as differences between x vector at nearest moment of time, and the thermodynamic temperature is defined as integral over temperatures at moment t. So it's averaged temperature over some period of time called tau.
And temperature is defined as kinetic energy averaged over time. Yes, that's what you're saying.
Yes. Energy is and divided by the dimensionality of trainable variables, by number of all trainable variables. So using the seventh and eighth form, eighth formula in next in experiments and other and other analytics, these authors use this formula to calculate the temperature of system. And then I told about this formula is used for calculations during the experience also. So one moment, yes. Also, I missed that this here at the end of the slide, I used terminology individual particle motions, and I need to know that the analog of particle in mechanics, authors said that this is just some concrete trainable parameter. So they called the concrete trainable parameter as particle. And after this, authors describe the equilibrium.
It's like one-dimensional particle. Are you saying that they're talking about one-dimensional particle? Each trainable parameter is one particle. That's
yes. They use this terminology. They explains. Yes. So next goal is to define the equilibrium state. Equilibrium state and to find the similarity between equilibrium state in thermodynamics and equilibrium state in machine learning. As we know from machine learning, that equilibrium state is some state where loss function doesn't change in average or change with small fluctuations. And they use also the definition and their idea correlates that all macroscopic parameters, loss function, and temperature at the equilibrium state will not change, and can changes only with small fluctuation. For example, as we understand the average value of velocity will be equals to 0, and ninth equation shows us the principal differences between gradient descent and stochastical gradient descent. As we understand, in gradient descent, we will come to minima of loss function, and then will not be any at the equilibrium point. There will be fluctuation also for the mean value of v in square. But for stochastic gradient descent, when we use averaging by many batches and they are randomly, we will have this non-zero mean value of square velocity. So using this fact, we can make next idea that gradient descent describes the system which comes to temperature to zero temperature means in thermodynamics Kelvin 0, so there are no motion of particles, but stochastical gradient descent told us that the system goes not to 0 but some constant temperature. So due to the non-zero average value of square of velocity, and this moment told us that that when we use gradient descent, we will come to the minimum of potential energy. But when we use stochastical gradient descent, we will come to a minimum of not potential energy, but free energy. As we know, free energy is the thermodynamical potential, which we can calculate from energy as F is equals to U minus T multiplied by S, where S is entropy, and so S entropy term describes the fluctuations and other stochastics that comes us from stochastical gradient descent, and so that's why a stochastical gradient descent describes the process to equilibrium and minimum of free energy, not potential energy. Arthur told us about it and explain why it is true. Now I'll tell about the experiment which authors used to find the dependency between temperature and hyperparameters such as learning rate and batch size. And the data set which they use was MNIST data set. They also use another data sets, as they told us in this section, but the plots were shown for the MNIST data set, and they use the Linnet modified architecture to work and to calculate this architecture is used by authors in experiment. So they use as an optimizer stochastic gradient descent. They use regularization of it, and on the next slides I will show you different plots for different values of learning rate and mini batch, and I need to know that next slides will show us not total temperature of the system, take into account all trainable parameters of all layers. We will see the temperature of different layers. That means that they calculate temperature only for trainable values, for example, for first convolution layers, second linear layers, and others. So they they don't write formulas how to calculate, but we understand that we need to take not all of the trainable values, but only trainable values which used in the concrete layer. And first plot is how the temperature depends on inverse mini batch. Inverse mini batch is the parameter 1 divided by batch size. And we see that for different layers there are different behavior of this temperature, and they fitted it through a power law and provide us the parameters of this power law. Also, I need to note that we are talking about temperature at the equilibrium. So at the end of the drawing, they see how the temperature depends on on hyperparameters. And we see that at the next slide, we see how temperature depends on a learning rate. So they make several tests with different learning rate and show us the temperature of the layers as a function of learning rate, and we see that they also fitted this power law, and different layers have different behavior, different dependency between temperature and learning rate, as we see it at the previous page when we looked at the dependencies between temperature and temperature of layers and mini batch. So what the conclusions from the experiment do have authors? At the introduction, authors told us that they were looking for the analytics of other authors, and other authors provide the next formula for temperatures. Temperature is depending as square of learning rate divided by batch size, and using this the experiment on the architectures that current authors provide, we see that the dependency is more complex, and can't be explained, can't be proportional to square of learning rate divided by batch size for every layer. And the main conclusions that authors find through this experiment is that each layer has its own temperature and its behavior is quasi-independent. The total thermodynamics system can be considered as the set of subsystems which are described by the layers. The second the result is that dependency between eta and beta is non-linear. So some layers show linear behavior, some non-linear, and this is this is for them this is a good result. For they notice that result because it's different from other previous authors which they looked at the introduction.
So have they proposed? So they have they proposed any phenomenological form for this dependence?
It's they don't provide us a form with beta and t in general, but as I understand, they propose the form of profile of in the individual plots as power laws with different
Powers. Okay.
Powers, yes, and they say that generally they need another model to make an analytics, and so next slide will tell you about model which they propose, but this model, but they haven't any other results using this model. As I understand, at 2021 year, it was just an idea. Maybe we will see some papers about it later. So the main idea that due to fluctuation and non-conservative forces with gradient descent, authors say that we can't use a classical Hamiltonian, which I define as H with index match as the sum of kinetic and potential energy, and they say that we need to add to the Hamiltonian another term called dissipative term, which depends on entropy.
Hold on, Artem. They haven't used classical Hamiltonian because they got rid of velocity. They set the velocity to 0. So they haven't used the Hamiltonian dynamics at all.
Yes. I agree with you. In this paragraph, they provide an idea how to look.
Okay, so they're saying let's extend the dynamics to have a Hamiltonian, and then let's add another term which corresponds to the entropy.
Yes, they say that their idea is to add to classical Hamiltonian dissipative term, which depends on entropy, and their first approximation of this term was just some constant multiplied by entropy. They don't define how do they want to calculate entropy of system and how this entropy of system defined. Maybe
I'm still confused because at one point they set velocity to 0, and the other point they define temperatures through velocity, through the kinetic energy.
No, they mean I want to say next that they say that
average.
That the idea is that, as I understand, the main idea is that between 5th and 6th equation is just to find an analogous parameter to learning rate in mechanics. And they said, if we suppose that term with velocity is small, the learning rate can be presented as a mass term. But they don't use the approximation of zero velocity in other formulas at 7th, 8th, and other.
That's fine, but in the simulations, if they use stochastic gradient descent, then velocity is zero, unless you use momentum. So do they do numerics stochastic gradient descent with momentum or not?
No, there are no information about momentum and no.
Okay, but then if they do use stochastic gradient descent, then velocity. Okay, so velocity is not zero, but if you want to equate it to Hamiltonian, it is zero, and so I think that point is confusing. But
yes, I agree with you. I think in generally that the main idea of these equations was to find to find duality between learning rate and mass, and using some approximations they find this, but
then they don't use it for the
yes. They in 7th, in 8th equation, in calculation of temperature for this slide, they don't use
that's just for the duality mapping.
Yes. Only for showing the duality between some parameters with some convictions. For example, if we set velocity to 0. Okay. So at the end of their article, they show us that using this additive dissipative term, which is proportional to entropy, which wasn't defined in the statistical, they can write the governing equation of this contact Hamiltonian system, non-conservative Hamiltonian system, and they finished at this point and say that this will be a goal of new researchers to make new experiments, make new analytics in this field, working with Hamiltonian dynamics with dissipative term. And so in conclusion, what I can say that authors shows us one of the main goals was to show the duality between stochastic gradient descent dynamics and thermodynamical system. They show us the way to calculate the temperature of layer or total entropy or total temperature of system through the velocities, which are differences between x vector of trainable variables. They make an experiment that shows the non-linearity between temperature and learning rate or batch size. And they proposed the model of Hamiltonian mechanics with dissipative term, which they called contact Hamiltonian dynamics, to use it in further research, further experiments that will take to account energy dissipation, entropy, non-equilibrium evolution, and others. That's maybe all that were interesting in this current article. Thanks for your attention.
Thank you, Artem. See if there are any questions. Let me just ask one. So in general, the only contact with thermodynamics that I saw is this definition of temperature through the kinetic energy. And it isn't even clear that this is how temperature should be defined, because usually temperature, it would be, gradient of the energy, internal energy with respect to entropy, right? That's how we do want to introduce, or as inverse of Lagrange multiplier in the context of statistical mechanics. So here it's more like of saying, well, in ideal gases, we do see the temperature is proportional to the kinetic energy. Maybe let's do the same here. So and that's all there is in terms of thermodynamics, because the other thermodynamic quantities were not mapped. Is this correct?
Yes, I
Pressure,
agree with you that in general, in general authors use only one thermodynamic function and define this thermodynamic function as temperature. They told us something about entropy in terms of the future research, but don't.
But we haven't seen that, right? We haven't seen the
but they don't define entropy and don't define how the same entropy will change the Hamiltonian.
Okay, so it's more like, that's what the thermodynamics might look like once we have everything incorporated. Okay, good. I think that's interesting. Other questions? All right.